Greetings, my name is Professor Duke Orata. We are continuing with our lectures, and today we want to look at isentropic flow in duct of varying areas. Flow, duct, now if you remember from our last lectures, and I keep encouraging you once again to go through our lecture systematically. In the last lecture, we developed that momentum equation, which gave us the sum of the forces involved, assuming there are no components in the y-axis, was given as mc2 minus c1. And you will remember, m is the mass flow rate, which we said was AC over V, where A is area, C is velocity, V is specific volume, and this is from the continuity equation. Continuity equation. So that's very important for us to note. So if we profile this duct, that's to draw a schematic of that duct. Let's draw it here. Let's call that plane 1. Plane 2, so we have the sum of external forces which are acting on those surfaces there can be threefold. The forces can be as a result of gravitational activity. So the forces acting the fluid between planes 1 and 2 can be one of gravitational in origin, the gravitational forces, it could also be as a result of hydrostatic force or hydrostatic pressure, where we have pressure 1 acting on surface A1, pressure 2 acting on surface A2. And of course, we also can have frictional forces as a result of shear stress along the wall. Shear stress. So these are forces which can act on that fluid or that liquid between plane 1 and plane 2. And of course, remember we said that the rate of the force was the rate of change of momentum, and that force will be acting, that change will be in the direction of that force. That's what we said in our last lectures, which again, keep encouraging you, go through our lectures systematically so that you follow the processes. Now, if we decide that we are going to focus on some element between plane 1 and plane 2, separated by an infinitesimal distance. Suppose we focus an element between planes 1 and 2, separated by infinitesimal distance. Separated by infinitesimal distance. In that particular case, remember, we have this duct where we say there's some pressure acting. Always remember, we have a pressure We have our volume, velocity, we have our area, and of course, we have some infinitesimal change, the pressure there, in the volume there. And we have, so of course we have our flow, that particular case. Always remember that. So if we focus on an element separated by some infinitesimal distance between those elements, let's call that infinitesimal distance between those particular elements, then in the differential notation, the momentum equation which we had, the momentum equation, don't forget, we say the momentum equation for this small section, we now have the various forces. Remember, we have PA on that face there. We have PA, that particular face on plane 1, PA. And why are we talking about PA? PA is a force, because don't forget that pressure times area is, pressure is force over area, multiplied by area leaves you with force. So the forces acting, we have PA, that surface, minus P plus dP, A plus dP, dA. And then of course, we have those forces which are normal to the wall. Normal to the wall. Let's call that theta, normal to the wall. So the forces which are normal to the wall, or perpendicular to the wall, will be given by P plus dP. That's the average of those forces, will be P plus dP over 2 dA. Because remember, these are forces which are normal. The wall. And in a nutshell, that particular force which is normal to the wall, ideally is P plus dP. The average of it should be dP, dA sine theta. That's sine theta there. Or can have the same expression, sine theta, and that will basically be still be dP over 2 dA. Very important for us to note that. And we are not going to focus on frictional forces, because for us to assume a one-dimensional steady flow, we will not want to assume that frictional forces are exaggerated or escalated in this flow, because it will lead to non-uniformity in the flow. Because if you consider, for example, the frictional forces between the layers, then again now, then there will be no uniformity in the properties, on the properties in the face, in the face of that particular fluid, which is perpendicular to the flow. So we want to ignore frictional forces. Very important for us to ignore the frictional forces. So let's just make a footnote of that. So we ignore, note that we ignore frictional forces for uniformity or properties for uniformity of properties perpendicular the fluid surface. Otherwise, it will be non-uniform, and then now our approximation for steady flow will be flawed. that one-dimensional steady flow will now be flowed. So we ignore those frictional forces. So the net forces which we have, the forces which we have specified here, that remember pressure and area is force, first on surface 1, surface 2, and of course these are the forces which are normal to the wall. And of course all this will be equal to mdc. And don't forget, m from the continuity equation we have already specified is AV over C, where that's area, cross-sectional area, velocity, AC over V velocity, and specific volume. Don't forget that. And so if we open up this expression and we ignore the second order components, or what we call their doubly infinitesimal components, let's open up this expression here. We will have, let's open up this expression now. So simplifying, we have PA minus, because remember we open up, this brackets, we just multiply the elements there. So we get PA plus PDA plus ADP plus DPDA plus, let's open up, multiply that, PA, PDA, ADP. You don't write DPA, no, it's ADP and DPDA. And then we have P plus P times DA will give us PDA plus DP dA over 2. And this quantity here, these are doubly infinitesimal. Doubly infinitesimal. And so you can assume they're zero. They're vanished. Because think of it in a local manner, in a simple manner. When you multiply small quantity to smaller quantity, you get even a smaller quantity. Multiply 10 to minus 7 by 10 to minus 6, you get 10 to minus 13, which is even smaller. So think of it in that manner, as a mnemonic for you to remember things. And so we have PA. So we'll have PA, so those are vanished. This PA will cancel with that PA. So we'll have, and we'll also have minus, because remember we have PA, let's just write it so that you don't get confused. PA minus PA minus PDA plus minus ADP plus PDA is equals to MDC. So what do we have here? So PA will cancel the PA, and of course PDA will cancel the PDA, and so we are left with minus ADP MDC. So what are we left with? So what do you have? We have minus A dP is equals to M dC. But remember, from continuity equation, that's the mass flow rate. That again is from continuity equation, I repeat. M is AC over V. So we can put that there. So we have basically AC over V dC plus AdP is equals to 0. And so we can further simplify this. We can cancel out the A's, divide throughout by A, and cross multiply. So dividing through by A and cross multiplying by V, we will have CDC plus VDP is equals to 0. Very important equation. Momentum equation. If you remember, look at our lectures, earlier lectures, where we derived the expression for energy equation. Compare this is the momentum equation. They are basically look-alike. They basically look alike. This is the momentum equation. Compared to the energy equation, remember, for isentropic flow. And don't forget isentropic flow, because we said from Closures inequality, don't forget, ds was greater or equal to dq over t. So that when dq was equal to 0, that's adiabatic, then ds greater or equal to 0, that is isentropic. And so when we worked with that, from first principle, remember, from first principle, we were able to show from first principle, remember we said H is equals to U plus PV. And if you take the differential of that, then DH is equals to DU plus PdV plus VdP. And what is DU from first law? So DH is equals to DQ plus DW minus DW plus PDV plus VdP. And therefore DH is DQ. And what is that? From PV work, that is PDV. So that cancels with that, plus VdP. And so, under adiabatic conditions, when dq is equals to 0, dh is equals to VdP. Remember that? We came up with that particular result. And so, we came up with this particular result in our expressions. And so when we worked with this particular expression here, and we worked with the continuity equation, AC over V is equals to AC1 over V1 is AC2, A2 over V2. And we said that you could write that in the logarithmic form, that is natural log of A1 plus natural log of C1 minus natural log of V1. That would be a constant. That would be a constant. So we don't have to put the subscript and the subscript. In the differential form, this is dA over A plus dC over C minus dV over V will be equal to 0. Because remember that identity which we have always used, the identity we have always used as the integral of dx over x is the same as the integral of d ln x, which is the same as ln x plus c. And so, if we take that differential form, we have this particular expression here, in this particular case. Don't forget this quantity here. And also, we had from the steady state expression that dh plus dc squared over 2 plus gdz is equals to dq plus dw. So these are equations which we have worked with throughout. And so when we are talking of adiabatic flow, adiabatic conditions in a nozzle or a diffuser, this will be 0. Adiabatic in a nozzle or diffuse, remember that. And so we have dh plus dc squared over 2 plus gdz is equals to 0. And of course, we are assuming that the datum level is not significant, so the potential energy, because that's potential energy, you can assume is 0. So we have dh plus dc squared over 2 is equals to 0. And that dh we have already seen that dh, but dh, remember, we have already seen that dh is VdP. So what does it mean, VdP? VdP